Uranium. Naturally occurring uranium is composed of three major isotopes. Uranium-238. All three isotopes are radioactive, and the most abundant and stable is uranium-238, with a half-life of 4.4683 times 109 years. Uranium-238 is an alpha emitter, decaying through the 18-member uranium series into lead-206. The decay series of uranium-235 has 15 members and ends in lead-207. The constant rates of decay in these series makes comparison of the ratios of parent to daughter elements useful in radiometric dating. Uranium-233 is made from thorium-232 by neutron bombardment. Uranium-235 is important for both nuclear reactors and nuclear weapons because it is the only isotope existing in nature to any appreciable extent that is fissile in response to thermal neutrons. Uranium-238 is also important because it is fertile. It absorbs neutrons to produce a radioactive isotope that subsequently decays to the isotope plutonium-239, which also is fissile. No fission products have a half-life in the range of 100 to 210 Ka. Nor beyond 15.7 Ma. Legend for superscript symbols has thermal neutron capture cross-section in the range of 8 to 50 barns. F fissile M metastable isomer, primarily a naturally occurring radioactive material, neutron poison range 4 to 97 A. Medium-lived fission product over 200 Ka. Long-lived fission product uranium-214 is the lightest known isotope of uranium. It was discovered in 2021 at the spectrometer for heavy atoms and nuclear structure at the Heavy Ion Research Facility in Lanzhou, China in 2021. Produced by firing argon-36 at tungsten-182. It undergoes alpha decay with a half-life of 0.5 milliseconds. Uranium-232 has a half-life of 68.9 years and is a side product in the thorium cycle. It has been cited as an obstacle to nuclear proliferation using 233U as the fissile material. Because the intense gamma radiation emitted by 208 teraliters makes the 233U contaminated with it more difficult to handle. Uranium-232 is a rare example of an even isotope that is fissile with both thermal and fast neutrons. Uranium-233 is a fissile isotope of uranium that is bred from thorium-232 as part of the thorium fuel cycle. Uranium-233 was investigated for use in nuclear weapons and as a reactor fuel. However, it was never deployed in nuclear weapons or used commercially as a nuclear fuel. It has been used successfully in experimental nuclear reactors and has been proposed for much wider use as a nuclear fuel. It has a half-life of 1.592 times 105 years. Uranium-233 is produced by the neutron irradiation of thorium-232. When thorium-232 absorbs a neutron, it becomes thorium-233, which has a half-life of only 22 minutes. Thorium-233 decays into protactinium-233 through beta decay. Protactinium-233 has a half-life of 27 days and beta decays into uranium-233. Some proposed molten salt reactor designs attempt to physically isolate the protactinium from further neutron capture before beta decay can occur. Uranium-233 usually fissions on neutron absorption but sometimes retains the neutron, becoming uranium-234. The capture-to-fission ratio is smaller than the other two major fissile fuels uranium-235 and plutonium-239. It is also lower than that of short-lived plutonium-241, but bested by very difficult-to-produce neptunium-236. Uranium-234 is an isotope of uranium. In natural uranium and in uranium ore, 234U occurs as an indirect decay product of uranium-238. But it makes up only 0.0055% of the raw uranium because its half-life of just 245,500 years is only about 1/18,000th as long as that of 238U. The path of production of 234U via nuclear decay is as follows. 238U nuclei emit an alpha particle to become thorium-234. Next, with a short half-life, a 234th nucleus emits a beta particle to become protactinium-234. Finally, 234 pascals nuclei each emit another beta particle to become 234U nuclei. 234U nuclei usually last for hundreds of thousands of years. But then they decay by alpha emission to thorium-230. Except for the small percentage of nuclei that undergo spontaneous fission, extraction of rather small amounts of 234U from natural uranium would be feasible using isotope separation, similar to that used for regular uranium enrichment. However, there is no real demand in chemistry, physics, or engineering for isolating 234U. Very small pure samples of 234U can be extracted via the chemical ion exchange process. From samples of plutonium-238 that have been aged somewhat to allow some decay to 234U via alpha emission, enriched uranium contains more 234U than natural uranium as a byproduct of the uranium enrichment process aimed at obtaining uranium-235, which concentrates lighter isotopes even more strongly than it does 235U. The increased percentage of 234U in enriched natural uranium is acceptable in current nuclear reactors, but reprocessed uranium might contain even higher fractions of 234U, which is undesirable. This is because 234U is not fissile and tends to absorb slow neutrons in a nuclear reactor, becoming 235U. 234U has a neutron